Hi. So the title of our talk is Going Native. I'm here with Michael and myself, Toby. So Michael, you guys probably know us from Oracle, and I'm from IBM. So some disclaimers. So today we want to talk to you about Project Panama. What is it? Why are we doing this? What's the purpose of this project? So in short, Project Panama is a better way to do native interop. Panama will allow you to describe native data types, like C types, vector types, variable length types. So you don't need to do the tricks like putting pointers and longs or using unsafe and byte buffers with tracking offsets to represent structures. Panama will provide you an easy way to do that. Also, Panama supplies a new calling mechanism. So if you want to use a native library, you don't have to write JNI wrappers for every function you're interested in. Panama will greatly simplify that process while leveraging the new types available. So you get caller safety and security. And with these things, you can take advantage of the new modern hardware that's coming out. A lot of these devices have C bindings or libraries that you can call to interact with. So Panama will greatly simplify that process. Before I go too far, I should say Project Panama will not be completed in 9. It will come in a later Java version. A lot of the work I'll be talking about is based on our prototype at IBM, and this will differ from Michael's prototype, so just be aware if you see some differences. This is very early, so a lot of this is just to explain abstract concepts, but it's not spec'd out by any means, so just keep that in mind. So I'm just going to give you a little overview of the major components of Panama. So there are header file extraction tools, a groveler. This is a tool to basically read in native data structures and headers. And this tool, as you'll see in the next slide, will output a layout description, which will be used by layout runtime. There's also the layout description language. The purpose of this is to provide a standard way to describe native types. There are runtime libraries that let you access structured data on heap and off heap. And also native function calling mechanisms to do calls from a JVM to C++, and intrinsic types to leverage vector instructions. So here's kind of how it works. You take your native structure definitions and you feed it into the groveler. The groveler outputs layout description and interfaces. The interfaces kind of combine the layout and the carrier types through accessors. So that's how those two are linked. And the runtime libraries instantiate the interfaces, so you get layout instances, native library instances. Also, runtime libraries provide a way to allocate memory on and off heap, and also provide platform-dependent functionality. So here's a little walkthrough, just an example of what I just said. So on the left, you start with your native structure definitions, and then that gets groveled, and then you get a layout description and an interface. So this is based on my prototype, and this is not really what we think. This is a very early version of a layout description, so this is all subject to change. But it's just to give you an idea of how this will work. So you have your layout description, and then you have your interface, and for each member, there are 3 accessors, one to set, one to get, and one to get the address of. So here's a little example of how that works. And then this lets you, so this is just to show how you get to use it. So with the library APIs, you can allocate memory, and then get a layout from that, and then peek and poke at the bits. And then on the right is just an example of the equivalent that you could do in C. So at this point, I hope it's clear, the different pieces of PANAMA, how they sort of fit together. Now I want to talk more about the layout description language. I want to motivate why we need a layout description language, and what should be in it. So the basic problem is that we need a standard way to describe native types. Different languages have different types. There's C int, there's the COBOL comp5. Even on the same language, the same type has different layouts. Ints and longs in C will vary depending if you ILP64, LLP, or LP64. And then there are also these types that are types that are difficult to describe in Java. So we need a way of sort of getting all the layout information into a standard format that we can use. Also, we need a way to describe access behaviors, how to interact with the data. Different compilers have different behaviors for volatile. There are different rules for atomicity. So we want a way to capture this information so we know how to interact with the data in a way that's predictable to users. But we can't encode every type, access pattern, or access behavior in the LDL. So the goal is to come up with a minimal set of constructs that describe the behaviors we're interested in, while letting users build on top of that to do more complex things. So I decided to split the components of the LDL into three categories. Memory layout, which of course is very important. Access behaviors, how to interact with the data, and type information, how to give meanings to the data. Some of these are more important than the others, and some of these, I would argue, are not really essential to LDL. So for the rest of the presentation, I'll try to motivate which of these belong in the LDL, and which of these could go to different layers. So in terms of memory layout, I think it's clear that being able to describe where the data is very important. So to this end, we came up with some concepts to facilitate this. So the first is a container. It simply represents a sequence of bits where size is multiple of 8 bits. So very similar to a primitive. And then when you put these together, when you have a composition of these containers, you have a layout. Because we also, being able to interop with network formats is an important use case. We need a way to describe types that don't fit the 8-bit granularity. So we have a bit field, which is similar to a container, except there's no size constraint. It can be any size, but has to fit within a container. And then lastly, have a endiness rule where it basically describes which bytes are most significant in a container. Here's a little picture that kind of shows how it all fits together. So in order to get these types, you have to kind of combine it together. So here's some operators that let you do that. So composition basically takes a container and combines into another one. If you don't have a container to begin with, then it's just the first container. This internally increases the offset so that your next container starts after it. A nest is similar, except it takes an existing layout definition and inserts it, and then increments the offset by the size. The replicator operator just basically repeats an operation, and I'll talk more about that later on. And then the union resets the offset back to 0, so that lets you put containers in overlap, lets you overlap containers. And the pad operator increments an offset. So here's an example of a fairly complex struct. This is how you would use the operators to create these types. So the first two fields, A and B, are just basic compositions to each other. And then the third field is a nest, so you would nest that. The fourth field is an array. So you have an array of 8 bytes, so you replicate composition of a byte 8 times. And after that, it's a little more complex. We have a union. So we compose the first member of the union, then we use the union operator, which resets the internal offset. Then you pad your way back down, so now you're aligned with the first field again, and then you compose it. So now you have E and F overlapping. And then that's the end of the union. If you're keeping track of offsets, right now we're on a 4-byte boundary, and we have a 8-byte field coming, so we need to pad the rest on a 64-bit platform. So that's the pad 4, and then at the end, at the end we compose another 8 bytes. So, as I said, this is, is still in the prototype phase. It's nothing, I'm not proposing any specific grammar, but you can see even with these operators, it's very easy to compress this data. If we just change all these words into letters, we can get a very compact representation of layout. So now I'm going to talk about access behaviors. It's basically this describe rules for interacting with the data. So one of the concepts that's very important is alignment. This basically describes how you're allowed to allocate, load, store, and do atomics with a certain piece of data. We feel like this is something that should be conveyed in the LDL. I think it's a property of the layout and not the members, which means that it will let you overline in cases like compressed objects, or it'll let you underline with things like packed objects. Concepts like atomicity and volatility, we would argue that those are better suited for layers above the LDL. There's a lot of variation in how these things are interpreted, and we don't want to encode that kind of complexity. An option might be to use var handles to build accesses on top of layouts, or maybe provide some annotation mechanism to supply information that, depending on vendor, may implement or may not. But these annotations are not specced. They're just kind of like compiler options that you would add. So now types and names. Carrier types are basically Java representation of the data. I would argue that these are not essential for the LDL because this information is already contained in the interfaces, so there's no need to have that redundancy. Register types, as far as purely, if you purely want to describe layouts, these are not important, but when you want to start interacting with the data, these will be important for function calls. So this is one that we've not made a firm decision yet, but it's something that we need to think about. And then names, I would argue, are the same as carrier types. This information is already in the interfaces, so it doesn't have to be in the LDL as well. So next I want to talk about variable length types. There's some types that are difficult to represent in languages like C and Java. And there are some use cases for these types. Some of these types like Java class files or protobuf types are very hard to represent in traditional structures. So previously I introduced the concept called replicator. This was used with a static constant, so it's never changed. But if you use a replicator with a variable, then you can create a wider range of types, which I'll aim to show. So here's the first example we had, similar to the first example we had. It's the basic array where you have a replication, but it's fixed. So there's nothing special here. It's simple to deal with. But in this case, on the top, we have an array where the size depends on the field before it. So there are additional concerns we have to consider there. And in the second case, we have an array of these things. So we have an array of variable length things. So the issues here is how do you determine how much memory you need for it? You don't know this ahead of time. You kind of have to walk through it. What happens if you can change the repeat count? If you are aliasing this data, you may have instances where one has a certain view of the data and another has a different. So you could easily create inconsistencies. Also, access time will start to vary. This may come as a surprise. You access a field first time, it's fast, and then you access a field that follows, it's very slow. So a lot of things to consider there. And then the next example is cases where the size of the length of an array is not simply a constant or a member, it's an operation on a member. An example is the constant pool in a Java class file. It's not the constable count, it's constable count minus 1. Or on a TCP header, the options field exists if the data offset is greater than 5. So in these cases, it's not feasible to create variable length arrays for every different variation. So we need a way to kind of let users to provide that information and let the layout runtime pick it up. So here's basically what I said. Here is a solution that we were playing with. Basically, you would implement either a complex variable length array or a privileged one. The only difference is that the complex one takes in the value of a member, and the privileged one takes the pointer of the layout. What this would let you do is that you would implement this function and describe how to determine the length of the array. And then the layout runtime picks this up and just does the right thing. So here's an example with the constant pool. So in your layout description, you would say the length is determined by this member and this class. And then layout runtime puts the two together. And then when you want to determine the size, it calls your routine and uses that instead. Here's a more extreme example with constant pool entries. As you know, constant pool entries have many different types, and they all vary in size. So using the same approach, you can describe constant pool entries. So this is kind of where we are with variable length types. Still a lot of work to do. We need to determine how many use cases this covers. Is it a complete solution? Is this important for Java users? Do Java users actually care about variable length types? Can we do this while providing safety and performance? So there's still a lot of work to be done in the future on this. And there's a prototype on GitHub, if you're interested. This right now only does the simple variable length types, but I'll be updating that soon. And I'll put examples of the things I showed. And some more legal notices.
So I'm going to talk about two different things. I'm going to start with, let's see if I can find the right presentation. Here we are. So I'm going to start with the very personal disclaimer. I'm going to follow it up with a more personal disclaimer. So everything I say is a lie, but also, as Toby already pointed out, we are prototyping things and researching and playing around with things. So I'm going to show you some things today. Don't expect that to stick. Things will change. Names are, in many cases, unfortunate right now. It's just placeholders we came up with because we didn't know better at the time. So things will change. Deal with it. Did you know, by the way, that you can buy these glasses? They're actual sunglasses. They can't be folded. It's pretty, Amazing. Okay, so I'm going to talk more about the binder part of this and the runtime part of this, and then the second part of my part of this talk will be a demo of what we have. So it's not just slideware. We're going to want to show that we have something actually working as well. So the binder part is the thing that takes these generated interfaces and the associated meta information we have and generates runtime implementations of that so that you can actually perform these calls into native. So that's part of what we supply at runtime. We're also providing a few other different things. So for example, the library manager. So obviously now you're starting to play around with libraries more explicitly, and system load library, it's as much as that loads libraries, it's not going to be providing all the functionality we need. So we need to have a more powerful way of dealing with libraries. And as Toby also touched on, we need primitives or helper functions and things for allocating and dealing with memory and data. So allocating and accessing and all of these things. And again, I'm going to touch on a few of those things today. The things I'm going to show today will be referring obviously to types in various ways. Toby already touched on the fact that there is a difference between the native types and the Java types, the carrier type we use on the Java level to represent whatever we have in native. We've made in our prototype for now the simplifying assumption that if it's sort of spelled int on the C level, we're going to call it int in Java as well. And we're going to blindly assume that they're the same size and things like that. That's clearly not going to work in the long run. We need to make that way more flexible. But for the time being, and when you see me do things today, it's something to keep in mind that it's a simplification of the real world. These types that the whole concept of converting between carrier and native types, it will be building on the layout language in some way, shape, or form. And one of the things that we have introduced, and I think both Vladimir and Ian later will potentially be referring to, are a few new vector types. So to represent wider vectors on x64 platforms, for example, we have introduced something called long2, long4, and long8, and they're basically what you'd expect them to be. They contain multiple different long fields, but can be sort of treated like a vector. And we are currently translating the 256-bit vector type on the native side will be a long4 on the Java level, for example. But again, more work definitely needed in that area. So the binder prototype we have has a couple of major functions, major methods for weaving implementations, for taking one of these interfaces and providing something to you that you can actually use. We have the raw version, which is sort of the low level. It will give you something you can work with, but it may not necessarily be easy to use, if I put it that way. What we're also playing around with, and I'll show an example of this in the demo later, is something we call the civilizer, which will effectively take this very low-level API and up-level it. The canonical example here would be a C string. Clearly, you as a Java user of this library, of this functionality, want to pass in a Java string and have it be automatically converted in some way. But there may be other cases like that as well. So I'm going to show a couple of demos of that. The binder we have, somewhat simplified or very simplified, it takes a number of different arguments. So it takes, for example, the symbol address of whatever function you want to call or whatever variable you want to access, the layout of that on the native side, and the Java method type or the type we want to represent on the Java level. And then it magically weaves an implementation. And surely there are a billion different ways of doing this, but we generate bytecode, and yeah, that's about it, I guess. And as part of that, you obviously need to take whatever carrier types you have and split them up or do whatever conversion is needed to pass that eventually into the native function, placing things in registers and stack positions and whatnot. You need to obviously call the function, and then coming back, you need to do the opposite. And the return value needs to be boxed or whatever the operation is back into something that makes sense on the Java level. So I'm going to show you a few examples of that. Just to put it into perspective, I'm going to mention a few types, and I'm going to go through these slides really quickly. It's just to get sort of a feeling for what we're trying to achieve here. And again, type names may change and all that. This is not an inheritance chart in any way. It's a few types we have, and they sort of use, maybe the edges are more a has than anything else, but these sort of build on each other. At the bottom, we have something called a scope. A scope is, all these are, by the way, interfaces, but I'm also going to be talking about them when I talk about this. It's not just the interface, it's also actually the implementation in the background, because currently we basically have one implementation per interface. But the theory is that this, we've chosen to make them interface, and then we'll try to stick with that in order to make it easy to combine them in various ways. So a scope is something you can allocate memory from, somewhat simplified. It keeps track of the memory you allocated, and it also checks if you want to access the memory. It provides functionality for checking that the memory is actually still live, so that you don't use it after it's been freed and so on. We currently have two different implementations of this in the prototype. One called native scope, which is, well, it allocates memory in native using malloc or unsafe allocate memory. And we also have a prototype, I'm going to say at this point. We're not really using it in the binder explicitly, but there's one heap scope as well. And that's basically allocating a byte array and giving you the same functionality on top of that. So on the higher levels, you're not supposed to care really about where the memory is, if it's on the Java heap or native. You could easily imagine, and I started playing around with a scope that allocates memory in non-volatile memory. So in the backing implementation, you mmap a file or use the NVM library to get memory and so on. So on top of scope, we have something we call memory region. A memory region is a contiguous area of memory, and it can, again, be on or off the Java heap. Basically, it's a combination of a base pointer and an offset. Or if this memory region is in native memory, that base pointer will be null, and the offset is the absolute address. So this is sort of the standard two-register concept that we have in unsafe as well. And what the memory region does, in addition to using scope underneath to make sure that the memory is still live, is that it also adds bound checking on top of this. So we have an implementation called bounded memory region. And before any access is made to the memory, we make sure that it's bounded and all that. This is all an attempt to make sure that, again, it's back to it. We will still, I'm pretty sure, be providing you ways to shoot yourself in the foot. But we want to try to be better than just encoding pointers in longs. So, we want to provide these additional checks on top of it, and at least try to make the world slightly easier. There are challenges, I should say. We have something called a layout type, so this is the other leg now, which combines the carrier type and the native types and sort of keeps track of how those relate to each other and how they can be converted back and forth. Not going to say an awful lot more about that. A pointer then combines a memory region with a layout type. So this is where we sort of have all the functionality baked into a pointer. So we can do anything from access it and get data, but at the same time checking bounds and liveness. And also combine that with type checking, so we know that what we're accessing is the right thing. And the theory, some nice theory here, is that you can basically hand out a pointer to anybody, and you don't have to be afraid that this anybody does the wrong thing with it, because it's bound checked for you, to be proven. You can do the expected things with a pointer, I guess. You can offset it, you can cast it. One thing to notice is that if you offset a pointer, even if you offset a pointer outside of its bounds, that will still work. Because you can do the exact same thing in C as well. You can have a pointer which points into some weird memory somewhere, and that's fine, as long as you don't access it. And finally, we have something called reference, and reference is basically the same thing as a pointer. These are the exact same concept as you would have in like C or C++. So you have a pointer and you have a reference. Reference can't be null. This is what you use to get the actual data, and it also performs the checks. So again, that was a very quick walkthrough of the various types we have in the prototype today, which will hopefully be helpful when we go through the demo. So to summarize basically what this gives you is, and this is it's a made-up example. The syntax isn't actually reflecting exactly what's in the prototype today, but the general theme is still that you create this scope, and it's auto-closable, so normally we would expect you to do a try with resources. You allocate your pointer, and you do something with it. And in this case, the made-up part here is that I've allocated memory that is read-only, and why somebody would do that is questionable, but at least on line 3, you'll get a pointer. It's 42 bytes. On line 4, you're reading that. That's good. You'll get the reference. And you will, in the next step on line 5, I'm setting a value. But again, since the memory was read-only, we'll get an exception. You're not supposed to do that. On line 6, I offset the pointer. It was 42 bytes of memory. Now I'm offsetting it to 4711, so that's clearly out of bounds. But again, the pointer offsetting operation is okay. That is okay. But on the next line, I'm then trying to actually access the memory and dereference the pointer, and that's where I get the exception. And then finally, after the scope has been closed, the memory is actually now deallocated. And if I try to do the same sort of operation, I try to dereference the pointer and get its value, then I'll get some kind of use after free exception thrown. So that's sort of it in a nutshell. So it's outlining at least the sort of functionality we're trying to provide. I'll quickly also mention that we're going to have to work on various helper methods for converting between native and carrier types. And one of the ones we already have is something called a transformer, which does C or native strings to Java strings and back and forth. So converting a C string to a Java string is easy. It's allocated on the heap, so we don't actually need to care about scopes and things like that. But the other way around, obviously, we need to place this string, or we want to place this string in native memory so that we can pass it into C functions. And then we do need a scope. So converting to a C string actually does take a scope argument and converts or creates a native representation of that string. Okay, now for the demo. Let's see if the demo gods are with us. I have created a small copy of, let's say, a few key system functions that I'm planning on using. In theory, I should have used the groveler to just extract the system headers. However, it turns out that system headers are really complicated to parse. They use every trick in the book and then some. So we're still working on getting the groveler to parse them correctly and produce the right output. So what I did instead was just copy the necessary prototypes. However, I will be using the normal libc library in the background. So this is just a shortcut for creating the interfaces, groveling the interfaces so that I have something to play with. Okay, yeah, I guess I need to produce that as well. Let me do this. No, okay. I'm gonna go for broke. So I'm gonna run JExtract. Yeah, I guess okay, let me do that. It's a low-tech solution to this problem. I'm gonna keep scrolling up. Okay, so somewhere in the background, you'll just have to trust me. I ran JExtract. I gave it the header file. I asked it to produce a mysystem.jar with the groveled interfaces in it. And on top of that, I added a parameter saying all the interfaces should be generated into a package called myPackage. Okay, so just trust me on that for now. Oh, this is so gonna suck. How can this still be a problem in 2016? Oh, look, yes, excellent. Okay, that's the closest we'll get. PANAMA, demos, JVMLS, simple. There we go. Okay. So I'm going to launch JShell because all cool kids today use JShell for their demos, and I actually have a cooked command line. I'm going to give it some imports so that I don't have to do that up front. I'm going to feed it in this mysystem.jar file, which contains again the groveled interfaces. And then I'm going to, in order to work around an interesting issue I have with JShell, which is the fact that the binder is generating classes on the fly, but JShell doesn't recognize that fact. It doesn't know about these classes, and I haven't figured out exactly why this is yet. I've been trying to communicate or work with the JShell guys to see if that's something we can work around, but they are two different processes, and there's some magic going on. So what I have in the binder is something that spits out class files to disk as well, just as a debugging thing, and that makes actually JShell be able, can pick them up in the other end. So that's the rest of this weird command line. It's mostly just to get the demo to be workable. Okay, we have JShell. So the first thing we're going to do is load or bind that nice new library of ours. So as I said, we have groveled something like this. So the interface that got created from this header file I showed you is called MySystem, and it's in the package. And on top of that, we need to help the binder figure out, and this is something we're working on, improving. We need to help the binder know which library to look up symbols in. So I'm saying the default library. It's something that is already loaded. And again, this will change as well over time. OK, so we got an instance back. That's interesting. Let's see what it contains. For each. Okay, so we have a bunch of methods. Among them, we can see that there's something returning an int called getPid. We have snprintf, which returns an int, and so on and so forth. So we have an implementation now. That's nice. Let's use that. So I think it was $2. So we're going to call getPid, and it wasn't $2. It was $1. OK. Yes, we got a number. So is that the right number? Process handler, handle, current, get PID. This is the sanctioned way of getting the PID. And they match. Lo and behold, we've called get PID and we got the result back. So that's the canonical example. Vladimir showed this last year, so it's not exactly surprising that this works, I guess. More interestingly, maybe calling things like snprintf, for example. snprintf is interesting because, first of all, it produces a string. It also takes a string for the format. And then it's a var-args function on top of that. I'm not going to go into details. If you want to know more about how we've implemented var-args support, come to the workshop and ask questions. But I'm going to try to call that guy anyway. So we'll need a few things. I'm going to need to allocate some strings to pass into native. So I'm going to create one of these native scopes. And first of all, I'm going to allocate the target buffer into which we're going to produce the resulting string. This, again, syntax will change, so keep that in mind. Okay. And as you can see, we got a bounded pointer now, representing some native memory somewhere. The next thing I want to do is create the format string. And by the way, what I'm going to do here is put printf mypid is $%d. So we're going to do a 2C string of mypid is. And we're going to need a scope. So this is telling the transformer to take the Java string and in the scope allocate native memory and then copy the bytes, the characters into the native memory version of that. So now we should be ready to call snprintf. We're going to give it the buffer. We're going to give it the length of the buffer. We're going to give it the format string, and we're going to give it the actual value of the %d argument. And we got 16 bytes of string back. So let's see what we actually got. Let's use the transformer to convert to string the buffer we allocated. So this is now, remember, snprintf is actually outputting characters into the buffer we supplied to it. Now we're taking that buffer and converting it back to a Java string, and lo and behold, it's saying mypid is this and that. How many minutes do I have left? Negative 2 or 3. Okay, I think I'm going to do both things then. Or actually, let me skip the civilization layer. So I'm just going to say that another version of this is using bind instead. And basically, what you'll get is an instance where when you call snprintf, you can actually pass in the actual Java strings, let's say. I understand that there are questions immediately in your heads on how that works. And again, it's not foolproof in any way. It's a proof of concept thing we've done. But in theory, at least, you'll get a nice civilized interface which takes Java strings instead of these nasty pointer to byte things. So it's easier to use. So, okay, so the last part of this demo, if again the demo gods are with us the last couple of minutes as well, which they obviously haven't been so far, is it's something at least I find interesting. So I found on the internet a OpenGL demo. So if you know about OpenGL, there's a library called FreeGLOT, or GLOT in general, and that provides a very interesting primitive, which is a teapot. So you can, with a single function call, create a teapot without actually having to describe what it looks like. It's just a teapot. So what I wanted to do was to see if I could get that to work on the Java side as well. So on the left side here, you have the C implementation I found, and on the right-hand side, you have the Java implementation of it. So my goal was really to take the C code and make as few changes as possible to it, and still get it to compile and work. And the idea here is that if you squint, apart from the boilerplate import things here at the top, which, again, we may be able to do something about at some point as well, you'll hopefully see the same kind of code. On the right-hand side, yeah, it does look more like Java because there's some instance variable I'm actually calling these methods on. And the other interesting thing is I had to add an F here on the float constants because otherwise Java C will whine about truncation from double. But apart from that, again, if you squint and I scroll down here, it's going to look roughly the same. So hopefully if you either have C code, it's easy to convert it, or if you know how to write the C code, it should be equally sort of trivial to do the Java version of that. That's the theory, at least. There is some additional boilerplate down here for loading the libraries, which again is something we're hoping to improve over time and make more automatic. But if I go back to this guy, please, demo gods, be with us, please, demo. I'm sure it will pop up on the wrong screen now, just to make it more interesting. OpenGL, make run. So what I did was I ran the groveler on the GLOT files, I compiled the Java application, and please. No, okay, so wrong screens, let me drag this over. Here we go. Okay, this is the teapot spinning, called from Java, right? Yay! And yes, there's a very final remark on this. One of the interesting parts of this is we're obviously calling it a bunch of different GLOT C functions, but what we also are doing, what the GLOT library expects you to do, is to supply a few callbacks. So every once in a while, the library decides that it's time to repaint something or reshape something or whatever it is. We have, on the C side of things, that looks like this. You just pass in the name of a function. Well, let's say the idle function here is passed in as an argument. On the Java side, it looks very similar. And as a matter of fact, the idle function here is called on, it's an instance method. So without knowing, the GLOT library decides that it's time to call the idle function, and it calls a C function pointer that it has no idea will actually be calling back up to Java to an instance method. And there's some interesting magic behind this. What I should say is that we are likely to have to make this slightly more complicated for memory leak reasons. But that said, it's a proof of concept. So good, that was it, I think.